sometimes when you're trying to come up with a sequence or just looking into patterns and things, you find a rule and it turns out there is no next option. The rule you wanted just doesn't work. Here's a sequence I found in the OEIS, the Online Encyclopedia of Integer Sequences, that grabbed my eye because it's called the Infinite Trunk of Least Squares Beanstalk. And there's really not much more explanation than that, which is really, if that doesn't pique your curiosity, what will? It says it's the only infinite sequence. We haven't learned anything new yet. It said infinite to begin with, such that a0 is 0 and a of n minus 1 is a of n, the next term, minus the least number of squares that sum to a of n. So it said least squares beanstalk. We've got least number of squares again. And then there's no other explanation about what that means, how you work it out. I've just spent a few minutes doodling, working out what that means, and it's actually quite nice. One of the problems with the OEIS is because there isn't much space for explaining what you mean, the titles tend to be a bit oblique, like this one, and then you'd want a bit more motivation, explanation, links to things. I think the assumption is that you will have published something somewhere else about it, but no such link on this entry. So the sequence is, I'll copy it down, A2 7 6 5 7 3. If you're watching this when the OEIS has moved to 7 digits, hello person from the future, I wonder how far away that is. And it goes 0 3 6 8 11 15 16 18 21, and we'll stop there. Okay, so it said it's infinite. My ... is correct there. It's going to go on forever. Where do these numbers come from? What do they mean? Where's the beanstalk? So it says it's the only infinite sequence such that this particular rule is followed. So maybe there are other ways of trying to follow this rule that make a not infinite sequence. So that's intriguing. First thing to try out is it goes 0 3, so going 0 1 must stop. So let's try that. So I'll write my 0. We'll start with, let's try and make it a beanstalk, eh? So write a 0 here. I'm going to try and go upwards. That's what beanstalks do. Up to 1. So does that obey the rule? What's the rule again? I'll write it down. A of n minus 1 is an minus least number of squares, which is another sequence in the OEIS, so I'll give its number A002828, nice number of an. Right, so I know an minus 1, that's my 0, and I need to find an an that satisfies this rule, so a next term. So does 1 satisfy it? So if an is 1, the least number of square numbers that sum up to that is 1. 1's a square number, 1 adds up to 1. Okay, cool. So 1 minus 1 equals 0. Bingo. Now next, I need to find another number for my A2. So that's A0, that's A1. I need A2 to be something that if I take away the number of squares that add up to it, I get 1. I don't know off the top of my head how many squares you need to add up to certain numbers. We could try working a few out, I suppose. So we'll go over here, we'll go n and A002828 of n. Right, so 0, how many squares add up to 0? If I add up 0 squares, then I get 0. 1, 1, 2. I need 2 squares, 1 plus 1. 3, I need 3 squares. 4, that's a square number. I only need 1 square number. 4 is a square number. 5 is 4 plus 1, so that's 2. 6 is 4 plus 1 plus 1, that's 3. 7, 4 plus 1 plus 1 plus 4. 8, 4 plus 4, 2 squares. So, right, so this carries on forever. Right. I need a number such that the difference between these two things is 1. Can you see one? I can't. Now I've cleverly gone off the edge of shot there. So I'm going to go over to the left here. So this is the difference over here. I'll write down the differences. 0, 0, 0, 0, 3, 3, 3, 3, 6. A person might be inclined to think at this point, does this thing always go up? It's certainly not going to come back down to 1 again, because it's a theorem that every number can be written as the sum of at most 4 square numbers. OEIS says Lagrange came up with that. Nothing's going to have a 1 in this column, which is what I want. So 1 doesn't work. That is a finite beanstalk, which means I've got to rub it out. Excuse me. So we're getting there. I can rule out 2 by the same logic. Can't see any 2's in this column. It's not coming back down to 2. So we go 3. 3 is the last choice I could have had, because it's the last thing where the difference is 0. So in order for this to work at all, it's going to have to be 3. Sometimes when you're trying to come up with a sequence or just looking into patterns and things, you find a rule and it turns out there is no next option. The rule you wanted just doesn't work. Right, so next term's 3. That's my A1. So again, next I've got to choose the next term. What's my A2? So I want something that when you take away the number of squares counting function, you get 3. So I want something with a 3 in this difference column. My choices are 4, 5, and 6. And yet again, I'm going to use the fact that this differences sequence I don't think decreases. I'm pretty sure it doesn't decrease. So 4 is out, 5 is out, 6 will work. So just so you can, oh, hello. So A1 is 3, so A2, so 3 equals 6 minus that thing over there, the thing in the 6 column, 3. So 3 is 6 minus 3, works. Bingo. I've got, I think, a rough idea of how this thing works. So if I keep extending this table down, and I use the rule of, I try and look in the column here for the last term I had, then hopefully I'll always find something that works. I'll quite often have a few choices, so some of them might end up going down a dead end that won't carry on any further. So I'll get a trunk. And I think the beanstalk thing is the fact that I've got this infinite trunk that keeps going, but those other numbers that I could have tried from there, the other options from here, those might be branches coming off it. Those don't have to be infinite. I can have like finite little branches coming off. So does that work? Well, off 0, I tried 1, that didn't work. And I tried 2, actually, I'm going to do a bit of erasing again. Better. So does that work? I'm going to start with 0 much lower down now. 0. And I know that that goes up to 3, and then 6, and then looking ahead at what I copied off the OEIS, 11, 15. Is that enough to get the idea? Let's see. From 0, I could have tried 1, but it didn't work. And I could have tried 2. That didn't work. That's not a great 2. 3. So could 4 have worked from 3? Let's see. So 4 is the sum of 1 square. So 4 minus 1 equals 3. So I could have got there from 3. And the same with 5. 6, 7, where are we? 7 is the sum of 4 squares, so that comes off 3 as well. Whoop. Thought that might come from further up. So then 8's the one that works. Sorry, 6, and then 8. 9 is, I need to write some more bits. You know what? Let's go to the OAIS. Let's find this thing. There's a list of these. I want this table. So 9 is the sum of 1 square. Well, I could have said that, couldn't I? Stop there. Okay. So 9. Oh, let's do these differences. 10 and 11 also come off 8. 12 comes off 9. So we've got a branch that's like, it's not trivial here. We're going 2 steps along, but it will turn out to not work later on. 13, 14, 15 all come off 11. So the beanstalk carries on upwards from 15 infinitely. So there we go. That's the infinite least squares beanstalk. I'm glad I've made some sense of it. Now, there's loads of questions that this brings up that I'd really like to answer from here. I'm not going to do it now. How do we prove it's infinite? I think if we maybe know the fact that this thing is always monotonic, maybe so here's an easy question. Does every number fit onto this infinite beanstalk somehow? The answer is yes, because, well, sort of by induction. If I've got some really big number, I then subtract the number of squares that you need this function. I need to give this a better name. The number of squares counting function. Subtract that, I get a smaller number, which by induction I've said is in the beanstalk. So I've covered a good few things here. So I just need there to not be a gap of 4 in this thing here. So I don't know. Maybe that easy. Maybe I've got it. Maybe I need to do a little bit more thinking. Lovely beanstalk. Cool.